Good morning, everyone. Welcome back to the AI and Robotics seminar. Today, we are glad to have Jacopo to present his work on safe learning-based control for robotics and his physics-based simulation. So Dr. Jacopo is a postdoctoral fellow at UTIUS, working under the supervision of Professor Angela Solik in the Dynamic Systems Lab. Jacopo's research interests include reinforcement learning for robot control, distributed and multi-robot systems, probabilistic graphic model, computer architectures, and software engineering. Yeah, looking forward to your presentations, and feel free to take it over.
Yeah, thank you so much for the introduction. I'll start here. So first of all, good morning. Thank you for having me. Again, as it was just said, I'm Jacopo Panerati, postdoctoral fellow at the University of Toronto Institute for Aerospace Studies, working for Professor Shirley in the Dynamic System Lab. Today, what I'm talking about is safe learning-based control for robotics and physics-based simulation. This is the theme of my most recent research and the subject of the central part of the talk, which, however, also contains a quick overview of my overall research path, also to give some context on the reasons and the way I came to work on the subject. So the title of the presentation itself is a bit verbose, so I make this short premise right away. And I try to frame the problem of safe learning-based robot control, its challenges, and why simulation can help us overcome them. So most of the times I find myself speaking to a purely robotics audience, and maybe this is one of them. So I gloss over the necessity to motivate robots and robot control. As a reminder, certainly there are multiple reasons and trends, including aging populations, need for improved accessibility, the recent pandemic restrictions, that call for more and more automation of those physical tasks that have been traditionally assigned to humans. So the growing needs for robots also entails a growing need to design robot controller. And thanks to advances of machine learning, this is also a task that used to be manually performed by human engineers, and now has the potential to be partly or fully automated. And so if you want to be a bit meta, we can say that the goal is to automate automation. However, deploying machine learning on real robot systems, cyber physical systems, what we sometimes refer to as embodied intelligence, demands a great focus on safety, much greater than for purely database machine learning, especially if you want truly pervasive robotic application that can closely interact with humans, sometimes even just for regulatory reasons to have the system accepted. So learning safely, however, also introduces new theoretical challenges and can be limiting because as we constrain how a robot operates for safety reasons as it learns, this also impacts what it can learn. And there are also additional challenges that can come from cost, time, and efficiency. So the last 5 years or so, I'd say, I've seen an explosion in number of safe control and safe reinforcement publication. However, this has left us with what I believe is the open question of how can we reliably compare these approaches for meaningful insight and progress. So I'll delve into this more further into the talk, also hinting on machine learning and reinforcement learning specific problems such as reproducibility. But the argument I'll try to make is that creating increasingly realistic and fast simulation is a possible panacea for several of the challenges towards deployable learning-based robot control. I also have a second slide I want to dedicate to summarize the broader themes that appear in my research, as these are a subject that influenced my thinking over the years and led me to my current research focus. So, and every time I try to make this sort of retrospective, I bring up this quote from Søren Kierkegaard that life cannot be understood backwards, but it must be lived forward. And the other quote by Somerset Maugham that the gift for quotation is a serviceable substitute for wit. So I try to do that. So the first theme and my main research interest has always been that of autonomous decision making, in particular involving stochastic models and learning. I started thinking about this when I was working on self-adaptive computing, and this is part of my research that eventually led me to work with robots. And the second thing that I think is transversal to my research is that of fault tolerance and safety. And I originally started worrying about fault tolerance and probabilistic modeling of fault tolerance in the context of space computing systems that are affected by radiation-induced single event upsets. Then because of communication failures in networked multi-robot systems, and more recently as a I try to formalize and generally quantify what it means for learning-based robot control to be safe. And finally, the third theme in my research is that multi-resource, multi-agent systems, from multiprocessor systems on chip to mobile multi-robots. And I approached this theme because of fault tolerance, as redundancies is often used as fault mitigation strategies. But it was working with the multi-robot systems that are often a bit too expensive to prototype in hardware, especially if you think of swarm robotics that ideally looks at hundreds and thousands of agents. That eventually led me to work on simulation and simulation technologies, which are a primary component of the work presented here. I do believe that interdisciplinary is important for meaningful innovation, and also that working at different level of development stack from computer and robotic hardware to middleware and application software has given appropriate tools to pursue my vision of creating repeatable and generalizable learning-based robot control for the real world. So having established this common understanding of what the theme of the presentation is, what the subject of the research involved are, this is the outline for the rest of my talk. I'll try to give a quick bird's eye view of my education contributions up until 2020. Then I'll jump into what I've been working on in 2021 and motivated, and present some of the recent results obtained through this work. And I will also add a few words on the things I've planned for the next few months. And if I pace myself appropriately, I should also have 5 to 10 minutes for a few software demos to give a more concrete sample of the work I've been doing. This presentation should be rather quick, so actually interrupt me if you want, but there should also be more than enough time for the Q&A at the end. So just for the historical and geographical context, my undergrad in computer engineering was obtained at Politecnico di Milano. I was in a double degree program for my master's, obtained laurea specialistica at Politecnico di Milano in computer engineering and a Master of Science in CS at the University of Chicago. And I completed my PhD in computer engineering again at Polytechnique Montreal with an internship abroad at NII in Japan. So I then started my postdoc in the same lab where I completed my PhD when my then supervisor, Professor Beltrami, went on sabbatical in Tübingen and offered me to deputize for him on the first year and began visiting research in the second year with Professor Sabatini at University of Modena Reggio Emilia and at the European Space Agency Austrian Center in Cologne, Germany. And after that, I spent half a year as a research associate for Professor Prorock in Cambridge and came back to Canada for my current position in 2020 to work with Professor Shirley. So my research career started in the microarchitectures lab at Politecnico di Milano and the artificial intelligence lab at UAC. So the focus of my research then was self-adaptive computing, and in particular decision-making in multiprocessor systems. So at the time I showed how to use reinforcement learning to train policies capable of autonomously adjusting the number of computing core and operating frequencies to run application at a desired performance level. And this was work that we present in the ACM transaction on reconfigurable systems and technology and systems, autonomous adaptive systems, and the NASA ESA adaptive hardware and system conference. Then during my doctorate, I initially continued to work on multiprocessor systems, but shifting focus from the runtime to the design time. And first I wrote a quantitative comparisons of the Pareto sets returned by multi-objective optimization approaches, including heuristic and evolutionary and MDP-based techniques for the high-level design of multiprocessor systems on chip. Propose the use of hidden Markov model to model space computing systems that are subject to radiation-induced transient and permanent errors to improve their reliability. And this was work that we published in Transaction Design Automation Electronic System, Adaptive Hardware System again, and +1, and as well as a book chapter in Springer's Handbook of Hardware and Software Co-Design. So then I was still at Polytechnique, and I was motivated by Professor Beltrami, Professor Sabatini, and now Professor WPI Carlo Pinciroli, who had been a PhD student with Marco De Rigo, to apply my experience with fault tolerance and multi-resource system to network mobile multi-robots. And so essentially this is the work that constituted the bulk of my late PhD and early postdoctoral research. So in particular, I developed and deployed in hardware decentralized control laws to preserve global connectivity in the presence of communication failure in a network multi-robot system. And the methodology we proposed was based on spectral theory, the study of eigenvalues and vectors of the Laplacian matrix of a graph, and the observation made in the 70s by Fielder that the second smallest eigenvalue of a network graph Laplacian of a multi-robot system, for example, is a proxy for the global connectivity of the communication graph itself. And we also augmented our approach with a robustness component based on the heuristic estimation of the number of paths between each robots. And as far as I know, we were the first to demonstrate such an approach in real robots, in specifically 8 cameras, K-team cameras, using deliberate fault injection in their communication infrastructure. And we also work on follow-up work to compare different area coverage strategies. So we used a lineage of potential overnight oscillation, and we also automated the hyperparameter tuning of the control law. And this work that was presented ICRA twice, DARS, on autonomous robots, and robotics and autonomous systems. The team I was working in Polytechnic in Montreal also collaborated with the European Space Agency in a human-robot interaction study that show how autonomy in multi-robot systems can reduce human operators' cognitive burden. And experimental phase of this work we conducted in Lanzarote during Pangaea, which is an yearly field training campaign that ESA organizes for its astronauts. And the multi-robot system that we used was comprising of 5 DJIs and 100 quadrotors under the control of a single operator. And just as a curiosity, one of the operators was Matthias Maurer, who's currently in space right now. I think he's coming back in probably the end of Expedition 66, or maybe in a month or so. So, and the vision for this work was, of course, to demonstrate how smart human-robot interfaces and robot autonomy can be leveraged to make planetary exploration more efficient. And so, this work was published in the IEEE Robotics and Automation magazine. So in Cambridge, I formalized the problem of private flocking and proposed an adversarial training scheme to optimize a quadrotor team's ability to hide their leader robot. This work was loosely inspired by the ideas of GAN's generative adversarial network and adversarial privacy. And as far as I know, we were the first to frame a similar adversarial problem for private motion planning of multi-robot systems. In this work specifically, we use microserver SIM as a simulation environments, and the 2 intelligent agents that we played against each other were a convolutional neural network discriminator and an evolutionary algorithm tuning the Reynolds flocking hyperparameters. And this we presented in RAL and ICRA. So then finally at the University of Toronto, I joined the Dynamic System Lab under supervision of Professor Schöllig, and I've been able to put together my passion for flying multi-robot systems, my initial interest in reinforcement learning as a framework for learning-based decision-making, and my interest in safety assurance and fault tolerance to start and conduct the research that I'm presenting in the rest of the slides. So this is an overview of the work I wrote, presented, published in 2021, and what I want to discuss now. First one being Learn to Fly is a paper I presented the most recent IRIS in October, and it details the implementation of an open source physics-based simulation for one of multiple quadcopters with integration to the open source work as well of on reinforcement learning of OpenAI and DLR, the German Aerospace Agency. Which, as far as I know, is now probably the most state-of-the-art Python simulation specifically for reinforcement learning of low-level quadrotor control on GitHub. Also last year, we contributed a quite extensive review article on safe learning robotics, and this overlapping with obviously with the presentation Siki gave last week. It just appeared, I think it appeared online two weeks ago in the annual review of control robotics and autonomous systems, and it's available in a slightly extended version archive with more supplemental material and longer footnotes if you also want to check that version out. And again, you probably, if you were here last week, you heard this already, but it covers 3 macro areas. According to a taxonomy that we came up with, learning-based control approaches that learn uncertain dynamics to safely improve performance, safety-augmented extension of traditional reinforcement learning, approaches aiming at certifying safety of learning-based controllers. And the article also lists the open challenges of the field, such as needs for methods that can cover broader classes of systems, dealing with state estimation, dealing with computational complexity, as well as better understanding the properties of learned black box models. And finally, this is something we more recently completed. We are still open sourcing. Should submit probably this week. Decided to embark on the mission of creating simulation tools to fairly compare learning-based control theory and reinforcement learning in robotics using physics-based simulation. And so to do so, we created dream-style environments that also incorporate a priori positive imperfect knowledge of their dynamics. And new APIs for reproducible randomization of inertial properties and initial conditions. So as I said, this is something we are open sourcing together with a collection of baseline controllers from various areas, from iterative control to learning-based control, reinforcement learning, safe reinforcement learning, etc. And the starting point and motivating factor for this work, in fact, was a figure that we included in the review article. And to create this figure, we look at over 100 of the references that are part of the core sections of the article, clustered in the 3 macro areas of the taxonomy I mentioned before. And for all of this publication, we look at what different types of quantitative results they were providing. And this particularly span from abstract numerical example to real robots. With real robots being a minority, not so unexpectedly, because real robots are challenging and expensive. But the other potentially problematic aspect that we observed was that although physics-based simulation was potentially a valuable middle ground with a compromise between realism and accessibility and portability, there was still a serious lack of open source and standardized environments that could be used to compare different but control theory-based controllers and reinforcement learning implementations. So the situation was a little bit better just on the side of pure RL, where projects like Gene by OpenAI and DM Control by DeepMind existed. But even these, we found still lack many of the features that a robotics engineer specifically would like to see when implementing a safe control approach. And now, in the previous slide, I just made a practical argument for the use of simulation instead of accessibility. To enable fair comparisons, we want different researchers to run their approaches against identical problems. And doing this in hardware can be possible, obviously. But I also want to add 2 additional points on why simulation, I think, might be key to robot learning and embodied intelligence. So the first one, of course, as previously mentioned, being safety, because we can't risk a robot to damage itself, the environment, or humans as it learns. And the second one being time. So much of the existing success of machine and deep learning came from very large data sets that for robotics can still be too expensive in terms of cost and or money to collect in hardware. And so the idea is a simulation clock that can advance faster than a wall clock can help us mitigate this problem. So essentially the belief I hold is that open source robot simulation will support and accelerate the progress of robot learning more or less the same way that MNIST, KIT, Common Crawl, etc. helped with the advancement we have seen in the last couple of decades, essentially, with vision and NLP research. So, going to more practical implementation, to effectively support research, we have to keep in mind that our simulation should be realistic enough to be meaningful, which for continuous control is not necessarily the case of tabular and grid world environments that are common in RL. But also simple enough to appeal to a broad audience and enable easy to understand comparisons. And this is a point that was raised in a 2015 editorial in the IEEE Control System magazine by Jonathan Howe. And we also want to provide our simulation environments with all the features that both a controls researcher and the reinforcement learning researcher would find useful in implementing their workflows. So these are, for example, the ability to specify and evaluate constraints, specify the distributions from which to repeatably draw randomized disturbances to apply to inputs, states and outputs, inertial properties, etc., as well as a priori dynamics that could be leveraged by model-based approaches. And other safer environments had been proposed before by Google, OpenAI, DeepMind, but so besides AI Safety Gridboard, which is not a project for robotics, we also noted that Safety Gym only included abstract high-level tasks, and Real-World RL Suite did not provide all of these features that we might want at our disposal to compare reinforcement learning with learning-based control. Notably, as I said, for example, the a priori, even if partial knowledge of a system's dynamics.
Sorry, can I ask a question? Can you hear me?
Yeah, sorry. Yes, go ahead.
Perfect. Thanks, Jacopo. So I'm wondering if Safe Control Gym also handles scenarios where there are more than one sources of unsafety.
Multiple combined disturbances, yes. We can have inertial properties are not necessarily the one we would assume that are the ones in the a priori model, as well as noise on the state or input, as well as an imprecise initial condition.
No, I guess I meant more like typically we have a single cost function for what's an unsafe state.
Okay.
And I'm wondering if it's possible to have multiple, so that you have you already have a multi-objective optimization with a single
essentially
safety.
Yeah. Okay, maybe this could be not necessarily the entire answer, but possibly something I can help in. So yes, the API, as I'll mention briefly later, is retrocompatible with OpenAI Gym. So there is a single reward per step, but there is also the evaluation of all various constraints per step. So one could use those extra field to implement additional reward signals and value functions on the side of the controller.
Got it. Great.
I mean, that's how I would do it. If I understood what you were mentioning, that's how I would implement it with the API we propose.
Got it. Thank you.
Thank you for your questions. And obviously, this is live code, so feedbacks is very welcome, and implementation of new features is also something we're working on. So we can also take the conversation offline and maybe think of new features. So then in practice, implementation-wise, we made a few high-level choices. We use the open source physics engine Bullet for physics rendering. And the side I'll make here is that the scene of physics engine for robotics is, in my opinion, increasing a topic. I think it's definitely worth keeping an eye on. We have a DeepMind acquiring Jacopo and open sourcing it. It's not yet fully open source, but hopefully will be soon. So that's also a project that's very significant in my opinion. OpenAI shifting some of the gym tasks that were on Jacopo to Google's Prax engine, and NVIDIA, as we all know, I guess, working on Isaac Gym Omniverse and having its own PhysX engine. So second implementation point, we implement retrocompatibility with OpenAI Gym to support all the existing libraries already exist for RLs, like Stable Baseline 3, Riser Lib, Mushroom RL problem. Third, we use Cassidy-I or Casadi as a symbolic framework for the specification of dynamics and constraints, and this, at least in our intent, is one of the main points making our work, we think, more appealing and accessible to robotics and control theories that do not necessarily normally work with reinforcement learning environments. And furthermore, by designing injectable and repeatable mismatches between the symbolic dynamics that we provide as prior knowledge and the inertial properties that are fed into the physics engine, I think we are providing a way to recreate in a control environment one of the real life challenges of robotic algorithms. So thinking that the system works according to a certain law, but having slightly small mismatches in physical properties. And fourth, we decided to start out our implementation with two robot platforms. So the archetypal RL control problem Carpal, which is too often looked down as a bit too abstract or easy, and I agree with that. But it's also too common in the literature not to have it, because our goal is still to provide a comparison platform. So it should work with many of the existing research that has been already published, and often enough uses Carpal as their first demonstrator. And the robot is a personal lab favorite, so the quadrotor. And we use both of these platforms for two separate robotic tasks. Stabilization, which is, I would say, a bit more common in reinforcement learning environments, and trajectory tracking, which is a bit more challenging and probably slightly more common in robotics research. And then finally, we use yet another markup language, YAML, as a way to easily configure simulations. This is mostly a technical point, but I think it's crucial for reproducibility, which is a challenging machine and more specific reinforcement learning, and portability, which is important for creating a more equitable research playing field for research in this area, and also enhances portability when there is a lot of randomization in many parameter choices going around a single simulation. So on this slide, I'll try to quickly go over a little more detail on the software architecture of the project itself. So dynamical models of the robots can be any of these three platforms on the right. So Carpal, 1D quadrotor, moving only along the z-axis, a 2D quadrotor moving the x plane. For the configuration system, this is an example of a YAML file that can be used to recreate a single simulation twice. And so just as an observation, it contains specification of simulation properties, like the control and physics integration frequencies, but also of constraints and disturbances. The block diagram summarizes how the safe control gym environment interacts with a learning-based controller. So at the time of creation, the simulation provides initial observation, like a standard OpenAI gym environment, but also the a priori information on the robot dynamics, so the reference tasks, the cost function, to the learning-based controller. And again, we note again the priori dynamics might be exact or only partially correct in case the configuration file included disturbances in the inertial properties of the robot. Then interaction between environment and controller is the typical action input, say the observation loop of classical reinforcement learning or feedback control, with the controller sending the action or input to the environment, and the environment returning the state observation, as well as additional information, the reward, the termination condition, like in any real environment, and additional safety information, such as all the constraint evaluations. And with regard to performance, even at fine grades such as 1000 Hz sampling frequencies, we show that, at least for these relatively simple examples of mobile robots, we can achieve 10 to 20x speed ups with respect to the wall clock, even on a commodity laptop without a GPU.
Another question, sorry, and apologies if I missed this, but does the adversarial agent, can it provide essentially any distribution as a dynamic from which you can sample disturbances?
That's deterministic. So we would have to implement, like if you want to be stochastic, we would have to implement the stochasticity on the side of the adversarial agent, and then feed the deterministic input as an extraction. And it's in the implementation we have right now, it's only an external force applied to the center of mass of the robot. Got it.
And another question. So for Casari, I haven't used it in the past, but do you think it's capable of modeling, contacts?
So what we provide in Casari is only the a priori dynamics of the system and the constraints. So it wouldn't.
But it doesn't derive the dynamics for you.
Yeah, exactly.
I see. Got it.
So it's what one would already know about the system, possibly with inertial mismatches, and then the rest of the problem, if there are disturbances, is what we want to learn essentially with the learning mismatch.
Got it. But why did you have to resort to a symbolic language for specifying this?
We thought it was more appealing and intuitive and similar in terms of syntax to what it was used more commonly used in controls research.
But I guess you're doing it in order to be able to propagate derivatives throughout the model, or is it is there another reason?
Yeah. Essentially, it's fed back to the controllers. Then one on the module on the left, one can use it for optimization within their own controller. Got it. Okay, cool. Thank you. Within the framework, it's only used for the evaluation of constraints and feeding back the values of the constraints. Got it. Thank you. Again, thanks for your questions and the opportunity to clarify, I think. And even having new ideas on new things we could add. So I was saying this, we started open sourcing this at the end of 2021. At this point, all of the environment's code and several examples and experiments are already on GitHub. And there is a companion paper archive as well if you want to read it and get a quick start on how to use this work. So in practice, how we use this and what one can do with all the stuff we implemented and I discussed so far. So the first thing we did was to show that the simulation environments could support the development and test of approaches from all three of the sub-areas in the taxonomy I was mentioning for the Safe Learning in Robotics review paper. So and these are results that are in the Safe Learning in Robotics review paper. So for example, a model predictive control approach with Gaussian process regressions, using this in this experiments at the top of the slide, to let a quadrator take off and over at the desired position without violating a diagonal position constraint. A safe exploration strategy for reinforcement learning, in this case, stabilization of a car pole while respecting a constraint on the car position along the rail and compare against standard proximal policy optimization agents and two variation of the same agents with reward shaping. So using a slightly modified reward function to stabilize and also encourage respecting the constraint. And finally, a multi-predictive safety certification of an unsafe learned agent. And in this case, the unsafe learned agent is again a proximal policy optimization RL agent for car pole stabilization. In this case, the constraint is instead placed on the angular position of the pole rather than the linear position of the car. And this is the third experimental result for which I will show how to run the code quickly later at the end of the presentation. And so just this level of compatibility with very different approaches, I argue it's something we did to helping bring together the controls general community, which was the initial rationale for doing all of this work. And beyond that, is in the archive paper, we show that with this work we can venture into actual cross-field comparisons. And as a disclaimer, the results are shown were not fine-tuned for hyperparameters, so I don't want to make claims that any of the controllers here is performing to their theoretical best. But again, to reiterate, the point is to show that we create infrastructure to make this comparison possible in the first place, as they weren't before. And so here, for example, we implement a various controller, linear quadratic regulator in 3 flavors with the exact model, with a 50% incorrect model and iterative one. Again, GPMC, PPO, another RL agent, a soft actor critic, SAC, for 2 tasks, car pole stabilization and to the quadrator trajectory tracking of a circular trajectory in this case specifically. And so if you look at the graphs of the state variables over time, we can see that although with different performance levels, they're all successful in stabilizing the car pole and somewhat successful in tracking to the trajectory with the quadrator. Although we can already see that for these slightly more complex tasks, iterative LQR and GPMPC tend to do a bit better than vanilla LQR or the reinforcement learning agents. And in these plots, what we show are the delta between actual and desired state variables, so just lower is better. And what's even more interesting, I'd say, is to compare data efficiencies by looking at the learning regimes of different approaches. And for these same 2 tasks, so stabilization and trajectory tracking, The two plots on the right of the slide compare the average cost per episode of the learning-based controllers as the training progresses and collects more data. So, for traditional REL and for model predictive control with cache and process regression. And the x-axis in this case is logarithmic because the orders there are orders of magnitude of difference in between where most of the learning happens for these approaches. This is not a big surprise because the GPMPC approach does leverage the a priori model in our environments, while PPO and SAC do not. And so they need a lot more data to sort out the dynamics of the systems on their own just from data, and this disparity is even larger for the more complex quadratic tracking task. Then making further use of the safety API that we presented just before, we can do the same type of analysis, not just for learning, but also for safety while learning. And in this case, we looked at linear versus GPMPC and PPO with and without a safety layer correcting the action. And a safety filter based on a control barrier function. And then we compare how safe these approaches are in terms of number of constraint violation throughout at the end of their learning procedure. And so the plot on the left is similar to the previous learning curves, but it shows instead of performance against data collected, it shows constraint violations versus training data. And then when training is completed, we can also see how successful these training controllers are in actually respecting the constraints at test time. And again, this should not come as a gigantic surprise. The approaches that do leverage the a priori knowledge of the systems tend to perform a bit more safely with less training, with requiring less data because they can leverage some of the knowledge they already possess about the dynamics of the system. And then finally, for robustness, and by robustness here, I mean the ability to perform well in generalized test conditions that differ from those observed at training time. Our configuration system for the repeatable randomization inertia properties and disturbances is like the engineering bit that makes it easy to compare various learning-based controllers. So the experiments reported here on the right specifically are carpal stabilization tasks, in which the length of the pole changes on the left, or a white noise disturbance is applied to the control input. And as was hinting, the very practical advantage of using a work at this type of plots and experiments, it's especially easy to do because it only requires to exchange and reuse the same YAML configuration file for the simulation and swap in the controller. And of course, there is still work to do. Next steps I have on the to-do list. My to-do list are more controllers, more robot environments, predefined and reusable metrics for comparisons. Public leaderboards would be a nice feature to have, especially now that we also propose a competition based on this work. And so all the controllers that are actually listed on the slides is coming soon are ready. SST, RAL, RAP are ready in GitHub, and LQR, CBF should be hopefully soon. And this semester, as a group at DSL, we're using the software to support the controls in robotics course UFT, a tutorial on safe learning-based control for the industry partner vector, and we use it to propose and create a community-wide competition at IROS as a way to invite third-party contributions for new controllers. And okay, already 40 minutes. So at the end, okay, as soon as I'm done with slides, I'll just take a few minutes to show the few demos, and these are slides that refer to those demos. So how to download and install the software on a simple 2D quadrature trajectory tracking with a PD controller that uses the same parameters of the real-life controllers we have in the lab. Parallel to the software architecture. I'll go quickly on this one because I guess I'll show them live during the Q&A. A purely terminal-based example of the APIs. So that one with highlighting what's the retrocompatibility part to OpenAI Gym and what are the new information that we added in our interface, and this connection to the signals in the block diagram that I showed before. And one of the experiments I proposed, it's relatively quick to run live with the scripts we provide on GitHub, so I'll also execute that. And for those who are not as interested in the safe part aspect of control, but they wouldn't mind trying the reinforcement learning approaches on a multi-quadratic simulation environment. There's also the other simulation framework I presented at IROS, which I think was relatively well received by the community at the intersection of RL and robot control, because it was for quite a bit of time on GitHub. So it has been used, and it is being used for research. And beyond safe control regime, and setting aside for a moment the safety aspect and reconnecting back to my interest in multi-robot systems, the last few words on this presentation was dedicated to this work I have been conducting parallel in collaboration with the innovation cell of General Dynamics Land System Canada and MIDAX. And for this project too, I have also been developing an open source bullet-based simulation environment for cooperative multi-agent reinforcement learning in heterogeneous mobile multi-robot systems comprising of multiple UAVs and multiple UAVs targeted with the surveillance of multiple mobile or even invasive targets. And in particular for this simulation, I created the action space and reward signal to use reinforcement learning for the problem of task assignment, that is the mapping of the heterogeneous agents to the targets, as well as the more general tracking problems. So assigning agents to targets and finding the motion primitives to reach those targets. And using this framework, I compared the performance in the task assignment problem of PQSSE reinforcement learning agents again against random and greedy strategies, already showing that RL matches the greedy approach for the mobile targets, and even marginally outsmarts the greedy approach when the targets try to perform evasive maneuvers if followed. And using the same framework, I also use a PPO agent in this case for the single agent tracking problem for both the UVs and UGVs agents with mobile and reactive targets, showing how successful with different level of performance they can be successful. But besides that, the main reason for creating this latter simulation was that I want to develop a cheap and easy to replicate heterogeneous multi-robot systems with both a virtual RL environment component and a physical hardware counterpart, because I mean that was my observation opinion. There is not yet a good solution for this type of research, and so I based the robot models and action spaces in the simulation on the hardware and SDKs of DJI's RoboMaster series robots, the S1 mini tank, the Tal NTT quadrotor. And so one of the things on my to-do list now is to develop the software bridge to deploy in hardware the reinforcement learning policies learned through those simulations. And so to reconnect to this statement I was citing earlier in the presentation, I think the simulation benchmark we need to enable meaningful progress in robotic reinforcement learning. I need a delicate balance between realism and simplicity. But I believe that being on the forefront of this type of research is particularly important and can help me in the short term to devise the general methods to reliably use deep reinforcement learning to replace conventional hand design low-level controllers that are still used in mobile robots. Specific understanding how the factory designs sparse reward signals and assessing controllability of deep actor-critic agents. In the long term, realizing the vision of eventually creating repeatable and generalizable database robot control for real-life systems. And yeah, and the last slide, I guess it's this slide for the ICRA workshop we have coming. I guess Siki mentioned it last week, so I won't repeat myself. We should have a call for paper out soon. So if you are interested in this simulation data sets and sim real transfer for learning-based robot control, that's an opportunity, and we hope to see you there as well. I still don't know, it's going to be in presence or virtual, I'm not sure. That's my last slide, and I am almost exactly at time. So I'll stop sharing the screen.
Thank you, Jacopo. Thank you for the great talk. Yeah, and then comes to the Q&A section. Any questions from our audience?
I have another follow-up question.
Yeah.
So it seems like the types of safety concerns that this library is addressing are sort of disturbances to the controller. And I'm wondering if there are any other types of safety that it could accommodate.
I mean, if your example, obviously, I'll take inspiration for this. Yeah, I mean, when we broadly speak about safety, but we specifically refer to constraint satisfaction in state and inputs. And then the ability to more easily quantify and compare robustness. So, which is something in literature, and sometimes because it's so often done ad hoc by different groups and researchers, is, I would say, not so easy to claim that those results are. I find it particularly different to compare this when we look at robust SRL or some other extensions of those works. They all provide quantitative results, but how much meaning we can get from comparing these numbers, it's arguable, right?
Have you also thought about having the I guess the agent that creates disturbances for the policy to be optimized in a loop as well, so that you can have sort of an adversarial simulator that is optimized to the policy?
Yeah, I mean, I work on adversarial optimization for I've done some work in that direction as well. Obviously, then the problem always arises in that the results are very delicate and hinge a lot on either the interleaving of the two learning procedures or the strength that we give to one agent or the other. That's, so for this work specific case, we only try to implement the robust adversarial RL work by, I don't remember his name, Laurel Pinto, yes. And that was one of the things that we observed numerically. Right? And I don't know if Justin's on the call. He certainly is more. No, he's not here. But yeah. I mean, but that's also not in the paper. It just it says specifically that if we give too much power to one of the agents, and what power means for the agent definitely depends also on the problem itself, whether it's a carpal stabilization or pushing a quadruped. Like what's the effective number of the absolute value of the disturbance that can apply that could completely crush the effectiveness of their serial learning is different and problem specific.
Got it. So, so my first question about other types of safety. So it seems like, can you handle scenarios where there's a definite mismatch between the dynamics model that the policy was trained under and the mismatch in the simulator? And I'm not just talking about adding noise to the dynamics, but there's bias in the dynamics as well. So the actual mean of the dynamics, if you will, changes with respect to the training distribution. Do you handle that in your evaluations, or is it an additive noise to the dynamics?
No, I mean, for example, we cannot like the quadrature might have a different in the a priori model might have a different inertia matrix than the quadrature in the physics simulator. So it would react different. It would have turn rates that they're quicker or slower than one would have predicted from the a priori dynamical model.
I see. Got it. Thank you.
Thanks for your questions, obviously. See. I mean, and in the meantime, as I'm trying to think and showing some of the, again, the reason for showing a demo is just to show that the code is there and everyone should be able to run it relatively efficiently if they want to. And if they can't, send me an email or open a GitHub issues, and we'll try to fix it ASAP. Because the goal again was to provide a tool for the community.
Very cool. Any other questions? If no other questions, thanks the speaker again. Maybe let's stop here.
Yep. Thank you everyone for participating.